In this video, we're going to talk about geometric sequences and series. So first thing, if we talk about a sequence, each term is going to be multiplied by the same number, which we're going to call r, to the next term. R is going to be a constant, which we're going to be calling the common ratio. So this word is going to refer to our variable r. And this is what we are looking at for geometric sequences. The rule that we're going to have is the following. This is given to you in the formula booklet, where U1, same as arithmetic sequences, is your first term of the sequence. R is your common ratio. And then N always represents the number of terms. So if n is equal to 1, we're looking at the first term. If n is equal to 10, we're looking at the 10th term. So we're looking at the nth term. So it refers to which position we're looking at. So some common examples of geometric sequences are the ones that we have here. 1, 2, 4, 8, and 16. What we can notice is that every time we are multiplying by 2. One way that we can find the common ratio, if it's not as obvious, is we can always divide the term. So 2 divided by 1. So in other words, U2 divided by U1, and we're going to get our common ratio. And that would have been the same thing as dividing, for example, U4 divided by U3. That would have been 8 divided by 4, which would in fact be 2. So that's one common way that we can find the value of r, is dividing the term by the term that came before it. If we look at the other example here, we're multiplying by 3 each time. So we would have a common ratio of 3, and we would have a first term of 10. So we could write this as un is equal to 10 times 3 to the power of n minus 1. Very important to remember when you're dealing with geometric sequences, the exponent is only on the value of r. The exponent is not on our first term as well. So we're going to need to remember that when we do our calculations. Let's look at our first example for today. Example 1. Consider the sequence 8, 4, 2, etc. Show that the sequence is geometric. When we're dealing with show that questions, we need to arise to our answer. So if we're showing that it's geometric, that means that the progression needs to have a common ratio. So we need to find the common ratio r in order to show that it's geometric. So in order to find the common ratio, we can divide the terms together. So U2 divided by U1, so we have 4 divided by 8, meaning our common ratio is equal to r. So in order to show that it's geometric, we can say each term is found by multiplying 1/2 to the previous term. And we just showed that we have a geometric progression. Question B, find the general term un. Well, un is always going to be our first term, which is 8, times our common ratio, which is 1/2, and 1/2 is raised to the exponent n minus 1. And you can always test to make sure that you have the correct equation. If I test and I put, let's say, n is equal to 3. N is equal to 3 is my third term in the sequence. So my third term in the sequence should be equal to 2. So let's check if I did this correctly. U3 would be equal to 8 times 1/2, 3 to the power 3 minus 1. So in our calculators, we can ask our calculator was 8 times 1/2 to the power of 3 minus 1. And in fact, we do get 2. So we did that correctly. Good. And then part C. Hence, find the 12th term of our sequence. 12th term means that we need to substitute n by 12. And we're going to use our calculator to help us with this. Now a shortcut in our calculator, we can scroll up, click enter, and I'm going to go and change my 3 to 12 minus 1. And I'm going to have an answer which is 0.00391. Now, our question asks us to write it as a fraction. So in my calculator math, we're going to change this to a fraction, and we get the answer 1/256. And that is our first example. Example 2. The second term, u2 of a geometric sequence, is 44. So let me break that down. And the third term, u3, is 55. Find the common ratio. A. Well, in order to find our common ratio, we can always do u3 divided by u2. So u3 divided by u2, we have 55 divided by 45. 55 divided by 44, we get 1.25. So our common ratio is 1.25. B, find the first term of the sequence. Well, the first term of the sequence, there's a few ways that we can find that. We have u2. So u2, normally to go from u1 to u2, we would multiply by 1.25. But if we're doing the other way around, then we can divide by 1.25. So therefore, u1 would be equal to 44 divided by 1.25. So we're going to get that u1 is equal to 35.2. Now this is one way of doing it because we were given u2, so it's a simple question here. However, the way that we could have used the general term of the equation to solve this question would be un is equal to u1 times r to the power of n minus 1. We know this. So if we replace with what we know, for example, we know that u2 is equal to u1 times r is 1.25 to the power of 2 minus 1. u2, that's equal to 44. So I could have substituted the information that I know, and I could have used nsolve to solve this question. So math, numeric solve, and I could have write 44, and I would have x times 1.25 to the power of 2 minus 1, which is just 1. And then I click on solve, and I get that our first term is in fact a 35.2. So this method here is a method that's going to work all the time, right? So we're using our general rule in order to substitute in the information we know and then use numeric solve to find our answer. Okay, next up, example 3. The third term of a positive geometric sequence is 63, while the fifth term is 567. Find the common ratio and the first term. Okay, well, what we know is that going from u3, u4, then u5, we would be multiplying by r every step. So going from one step from u3 to u5, this is r times r, so we're multiplying by r squared. So I can write an equation to talk about this. u3 times r squared is going to be equal to u5. Well, I know that u3 is 63, and I know that u5 is 567. So I can use this and find the equation for r. Remember, we're told we have a positive geometric sequence. So when I square root, I'm going to be using the positive of that. So r squared is going to be equal to 567 divided by 63. And we're going to do that with our calculators. We're going to exit here. 567 divided by 63. We have 9. So r squared is equal to 9. So when I square root both sides, I'm going to have that r would be equal to positive or negative 3. But since we want a positive geometric sequence, we're going to use the positive value here. Good. Next, we have our common ratio. Let's find our first term. First term, we're going to use any one of our terms, and we're going to create the general rule. So un is equal to u1 times our common ratio, n to the power of 1. If I substitute in u5, for example, well, I'm going to have u1 times 3 to the power of 5 minus 1, and I know that this is equal to 567. So I'm going to go into numeric solve to find the first term, 567. So we have x times 3 to the power of 5 minus 1, which is just 4. And I get that u1 is equal to 7. Okay, let's do another example. This time we're going to do a word problem. So Caroline is starting a new job. She earns $48,000 in her first year, and her salary increases by 5% each year. Show that Carolina's annual salary follows a geometric sequence and state the common ratio. Calculate how much she's going to earn in her 5th year. Okay, lots of things we need to do here. So if on her first year she's getting 48,000, that means that our first term is going to be 48,000. Now, we need to first show that we have a geometric sequence. Since we are increasing by 5% each year, that means that in order for me to find the second year, I'm going to be taking the initial salary and multiplying it by increasing. So we're going to have 1 plus, and then whatever the percentage we're increasing. So 1.05 because we're increasing by 5%. And this would give us the salary she would be making in her second year. So therefore, our R value is going to be 1.05 because we are increasing by 5% each year. So this is going to be our first part of our answer. Therefore, we can write a general form for this equation, which is going to be that our first term is 48,000. Our common ratio is 1.05 times n to the minus 1. Calculate how much Caroline will make in her 5th year. Well, we can replace n by 5, and we are going to get how much her salary should be after 5 years. So we're going to have 48,000 times 1.05 to the power of 4. And her salary in her 5th year should be 58,344 and 30 cents. Okay, now a little challenge to finish up for today's video. Example 5. Here are the consecutive terms of a geometric sequence. Find what k is. Consecutive terms mean that they're following each other one after the other. So we could have technically u1, u2, and u3, or we could have u10, 11, and 12, right? They're following each other. That's what we need to know. Okay? Well, if it's a geometric sequence, we know that we can write any term in the form of u1 times r to the power of n minus 1. Okay. I know that going from first term to the next, I'm multiplying by r, and same thing for here, I'm multiplying by r. So I can create some equations. Well, I know that I can always express r by having one term divided by the term that comes before it. That's a definition of r. So r would be 2k divided by k minus 1. But r would also be 21 minus k divided by 2k. Both of these expressions represent what r would be. So if I write this, I could cross-multiply at this point. So I have 4k squared. So I multiply both sides by 2k by 2k. And then is equal to 21 minus k times k minus 1. And now I have a quadratic equation. And this quadratic equation, I'm asking myself, when is it equal to each other? So one way that we can solve this with our calculator is we can graph this as our y1, graph this as our y2, and go look for our intersection points. So in my calculator, I'm going to have 4x squared as my first equation, and then we have 21 minus x times x minus 1 as my second equation. I'm going to go ahead and graph that. I'm going to change my window. Let's try and do zoom fit, which is the 0 option. Okay, a little bit better. So we're interested in the intersection point. So let me zoom in maybe to the section that we are actually interested in. So I'm going to move my cursor a little bit, and we're interested in what's happening here. Good. Okay, we now see that there's two intersection points possible. So let's go and find them. Second function, intersection. They're asking me for my first curve, my second curve, and then I'm going to go and choose the first intersection point. So the first intersection point happens at 1.4 and 7.84, while the second intersection point, we're repeating the same steps, first curve, second curve, and now we're going to go towards the other point, is going to be at 3 and 36. Okay. Now we need to think which one makes more sense in our situation. So k would be this x. So k is either 3 or 1.4. And let's check which one works. So if we test when k is equal to 1.4, well, we're going to have our first term would be 1.4 minus 1, so 0.4. Our second term would be 2 times 1.4, so 2.8. And our third term would be 21 minus 1.4. So we would have 19.8. Now, does this respect our common ratio? Let's test it out. 19.6 divided by 2.8. This is 7. 2.8 divided by 0.4. This is also 7. So perfect. So for this one, we have 7 as our common ratio, and it seems to work out beautifully. Let's test if it does also for the value of k is equal to 3. So for k is equal to 3, our first term would be 3 minus 1, which is 2. Our second term would be 2 times 3, which is 6. And our third term would be 21 minus 6, 21 minus 6, which would be 15. So let's see if this works. 2 times 3, 6 times 3. This also works perfectly. So we have two possible values of k that will give us geometric sequences. So k can either be 1.4 or k can be 3 in this situation. And this was our challenge question for today.